Hi guys, so I'm back here with another one of these beginners lessons, number 3, and this time we're going to talk about resistors. Resistors are, I would say, by far the most common components you're going to see on circuit boards, and we need to know a bit about them. We don't need to know a lot about the maths. We need to know what are they, what do they do, what are they used for, what goes wrong with them. I mean, we're trying to repair stuff. How to recognise them, that sort of thing. So let's talk about resistors. So a resistor is basically a conductor that doesn't conduct very well. So it's not a true conductor like a piece of wire, but a piece of wire has some resistance, by the way. Silver, for a given diameter and length, silver has the lowest resistance, and other metals have more. Copper's a very good conductor, nickel and some other ones are not quite so good. So everything at the end of the day is a resistor. They just have such a low value we call them a conductor. So resistors themselves tend to be, originally the first ones were made from wire wrapped around and around and around a ceramic tube usually, and these are called Wirewound resistors, and they were used various metals, but a very common one and one used today is something called nichrome, which is an alloy of nickel and chrome. It's 80% nickel, 20% chrome, if you really need to know that, which you don't, but it's nice to know. And basically the thinner the wire and the more you wrap around the tube, the higher the resistance. But nichrome is a reasonable conductor, so you can't get very high value resistors by wrapping wire. But for the use of them, you don't really need very high. Another very common material used for resistors, certainly back in the day, was carbon. Carbon's a very good resistive material, and literally they use blocks of carbon. Sometimes with impurities in it will affect the resistance somewhat. And resistors were made out of carbon for many years. Those are the first ones I saw. These days, metal film is quite often used for resistors. The through-hole ones again are on a ceramic type base, and the metal film is deposited in a spiral, and by altering the composition of the metal oxide films, you can get different value resistors again. So that's the common ones. Bit of nostalgia. I first came across resistors in the very early 1970s, when I was young, and I mean, back in them days, we used to just go playing over the fields where we lived. We had a lot of fields and waste ground. I mean, by waste ground, I don't mean like dumps and tips. It was just like ground that wasn't, probably it must belong to the council, I guess. It was just waste ground. You'd have the streams running through, and we'd all go in bits of woods, and we'd all go running around and playing in there, and we had scrapyards, and like these, not like these days, where a scrapyard is kind of like behind a big fence to stop people stealing the stuff. Them days, the scrapyard was just like in a field you could just walk into it, and we had one near us, and it was great. It had pots of old steam engines in it, and things like that. So it had some old wartime stuff in it, parts of tanks, and like these funny little cabins with little signs in it. You figured out something to do with radar installations in the wall. And we used to go playing over there all the time, playing and sitting in the scrap cars, thought we could drive them. I'd be like 10 years old, I guess then, 10, 11, something like that. Anyway, like one day I found a scrap radio, valve radio, tube radio, I suppose the Americans would vacuum tubes. And like there was no tubes in it, by the way, because like anything like that them days was lying around in the fields. The kids would go and nick all the tubes, the valves out of them, and we used to throw them at each other like missiles, because when they hit the ground they go pop and explode, well, implode. So we used to do that. But anyway, I took this valve radio minus the valves home and we had a shed in the garden, and in the shed, and I started playing around with these, and like inside were all these stripy things. Oh, they were colourful. Still, it's like candy. It looked like candy. All these things with all bright stripes on, and I didn't know what they were. These stripy things. I called them buggers. Oh, them buggers in there. I didn't know what the word bugger meant. It's just something I did one of my aunties say to the kids. Leave it alone, you little bugger. So these things were buggers to me, and I probably took a pair of scissors, wouldn't even have wire cutters, and started cutting, these things out of the radio so they got legs on, and ended up with a little tin of them, these stripy little things, these buggers, and started. I had a scale electrics, and I had a model railway. I had a transformer for the model railway, and it had like 2 terminals on with screws on, and I'd get all these little buggers, and I'd like connect them across the terminals, and then like put a cardboard box over it and get a long pole, so I could get like a good distance away and press the power switch to see what happened. And I was like hiding off behind the sofa, with a peering around the corner, pressing the switch with a stick, a mop, or something. And mostly nothing happened. But one or two of them, the transformer make a loud buzzing noise, and they'll sort of noise. And you switch it off. Well, that does something. You go to disconnect it, you burn your fingers. Bloody hot that is. And I figured out actually if you leave them on there long enough, you could get some smoke out of them, and that's what started me in electronics. That was my very first, at a very young age. And I think it's the fact it's all so colourful and stripy and look like candy that got me into that. Anyway, I digress. I hope you skip that last 5 minutes if you don't want to hear the nostalgia story. But anyway, resistors. Resistors effectively obey Ohm's law, and we know if you watch other videos, Ohm's law, VIR, yeah. And Ohm's law says that V equals current times resistance, yeah. And basically speaking, if your current is 1 amp, yeah, and your resistance is 1 ohm, which is R, then your voltage is going to be 1 volt. That's what Ohm's law says. Basically, the more voltage for the same resistance, the more current. The higher the resistance, the less current, and so on. So that's Ohm's law. So, what does a resistor actually look like in a circuit? Well, the symbol for resistor basically is this one. Yeah, there's 2 in common use. There's that one, and there's this one. Yeah. And those are the 2 common symbols you'll see on a circuit diagram, a schematic for a resistor. And as I say, resistors are measured in ohms, and commonly they go from less than 1 ohm, about 0.1 of an ohm, you don't see much less than that, sometimes you do, up to about 1 million ohms, 1 mega ohm. That's the common values that you see in resistors. So, on a circuit diagram, you used to see them marked something like this, so they'd say like 1 ohm, yeah? Or you see them marked where they say something like 2.2 kilo ohms, 2.2 thousand ohms, which is the same as 2,200 ohms, yeah? And that's how you used to see these marked on circuits, but sometime, I'm not sure when, I could look it up, but I noticed sometime around the end of the 70s, early 80s, they started marking them differently. And what they would mark them as, that 2.2 kilo ohms would just be marked as 2K2. Huh? This 1 ohm would be marked as 1R. And that's how you would see them marked. You'd have like something like 1 MO, which is 1 mega ohm, 1 M5, 1.5 mega ohms. So that's how they tend to mark them these days in circuit diagrams. Basically, they replace the decimal point with the letter for what it is: R for ohms, K for kilo ohms, and M for mega ohms. So that's how they're actually marked when you see them on a circuit diagram. So let's have a look at, with a bit of theory there. Let's have a look at some resistors and see what sort of things we have, yeah? So let's have a find here. What have I got? Let's put them under the microscope. Let's have a good look at them, eh? Let's see these proper. Just one moment. There we have the microscope. Yeah. Let's have a look what these things look like. We'll do a little bit more theory afterwards, but let's see first what do we have. Let's focus. Well, first of all, we need some resistors, don't we? Right. So I couldn't find any carbon resistors in my stash of stuff, but that's a resistor. it's probably about a 1 watt. I mean, they have. I'll come to wattage in a minute. Resistors have two values, but first we'll just talk about the ohms. Yeah. So that's a resistor. That's a resistor. Almost certainly a metal film resistor. That one, metal oxide. Here's another one. Bit smaller, yeah. And you'll see these have got coal stripes on. These are like them buggers I found in the radios, but them buggers were a lot bigger buggers than these, yeah. So these are values. Now, we used to learn all this, and you don't need it. But basically, it goes black as 0, brown as 1, red as 2, orange as 3, yellow as 4, green as 5, blue as 6, violet as 7, grey is 8, white is 9, yeah. And then the gold and silver are times 0.1 and 0.01 as a multiplier. So these are 4 codes. So in this case, the gold is actually the tolerance. That's how accurate that resistor is, yeah. Because when you make a resistor, it's not exact. So they more come like, you know, the value it says plus or minus 10% or plus or minus 5%, yeah. So just look at these now. We used to look at these. So we go red, red, black. That's 2, 2. Black is 0, and the third one's the multiplier. So that's 2, 2 times 0. That's 22 ohms. Yeah. This one here, this is orange, orange, orange. So this would be like orange is 3, with 3 zeros following it. So that's 33,000. That's 33 kilo ohms. And I think gold's 5%. I'd have to look it up. One more. So this is like brown is 1, black is 0, and red is 2 zeros. 1000, 1000 ohms, 1 kilo ohm. And we used to remember that, and it's only worth learning that for speed, because you can go on the internet these days, and for a 3 or a 4 colour striped code, you can just type in, you know, the colours, and it tells you what it is. And also modern resistors don't really tend to have these stripes, so you won't always see these in things that you're trying to, you know, repair. So that's some resistors. But we have other sorts of resistors. This one is a little Wirewound resistor. This is marked 22E. It's Russian. That's an I. That funny backwards front end is actually an I. That'll be 22. I know it's a 22 ohm resistor. I mean, if you're not sure, you can just get your meter on resistance mode. Just measure it, you know. But that's a 22 ohm, and I know these are little Wirewound type resistors. What else do we have? Here's a bigger one. Too big to get under the microscope, yeah. That I'm pretty sure that's another Wirewound. Look, this is marked here 10k, 10 kilo ohms, 5% the tolerance, yeah. And the rest would be manufacturers, and it was probably made in the 8th of February 1977. That's probably what that little code means. But that's a 10k Wirewound resistor. I've got a couple more. These are ceramic resistors. Up here. So these are higher powered resistors. Basically, they're made of ceramic. Inside here is probably Wirewound. 5 watt, 1.8 ohms. That's marked the old way. You might say that's saying 5 watt, 1 R8, which is the same as 1.8 ohms, just uses less letters. The J will be the tolerance. You can look that up and see how many percent tolerance of J is. Some more of these. Yeah, it's a 10. Interesting. This one's marked the other way. There you go. That's great. So this one's 10 watts, 4R7, which is 4.7 ohms. J is a tolerance again, yeah? Same sort of thing. It's got like a ceramic, and inside here will be like a long ceramic bobbin with wire wrapped around it. And then it's kind of sealed into this ceramic thing, so that's one of them. Couple more, but I'm sure they're looking much the same now. Zycon will be the make, 5 watt, 0 ohms, 22. Or you see that if you use a 0 with an ohm symbol here, often rather than saying 0.22 ohms, you put 0 ohms 22. So the symbol just replaces. Whenever you see a symbol, it's the decimal point. You got to remember it that way, yeah. That could also be put as 0R22. It would be the same resistor. It could be 0.22 ohms or 0.22 R, but you're less likely to see them marked that way. So that's that one. One more. This is a big one, isn't it? Yeah. These things, called golden droppers. Is the name for these. That's inside. This is a ceramic tube again, with like an epoxy or ceramic. It's probably ceramic in there. In the middle's like again a bobbin with a long piece of wire, and then it's all armoured in this aluminium, and you can see it's got a hole under here, yeah, another one there, and this is meant to be bolted down to a piece of metal. Reason being, resistors can get hot, and I'll come back to that in a bit, why they can get hot. This one's marked 100W, 100 watt, 2 ohms, well that could be, again, that could be 2R, but it's 2 ohms in this case. J, again, is a tolerance. You see, J is very common. I ought to go and look that up, but you can do, you know. So those are regular resistors, and these are all through-hole resistors, yeah? Then we get some more unusual, if you like, resistors. So the first one we'll have a look at, we saw these the other day. Can we get into the film? Where are you? Yeah, some of this bag here. We saw these the other day. If you watch the video, we found on this second disco light. These disc-shaped things, these are thermistors. These basically, they come in two sorts: negative temperature coefficient and positive temperature coefficient. Most common are the negative ones. Negative temperature coefficient, NTC, negative temperature coefficient, and then the NTC 10 will be like the model number, and you'd have to then go and look this up. 0626 is probably a date code, 6th of the 2nd or 2nd of the 6th, 2006, just guessing. But with these you can go and look up the code. So these thermistors, these will basically the resistance changes with temperature. Two main uses for this. One is as a temperature sensor. It can be used as a sense temperature, although often you use a thermocouple, but it can be used for that. But most commonly these are used for surge, stopping the surge current. When you first switch a device on, you get a big surge of current going in to charge all the main capacitors up, and these are used as surge limiters. Just so they start off as maybe 3 ohms. The current starts to rush in rush limiter, so it rushes in charging capacitors, and as it does so, it warms the resistor inside, and the resistance drops. So after a few seconds, it drops to like 0 near enough, and the thing effectively isn't there as far as the circuit's concerned. So those are thermistors, yeah. What else do we have? We have, let's see, we have these ones, these blue ones. These are disc shaped again. Let me just get one out. Let me get one of these for you. Here we go. These things. These are varistors. They look, if you recognise components, they look more like a capacitor. They look also a bit like that thermistor, but it's a varistor. These are effectively a non-linear resistor. They don't obey Ohm's law. In some ways, they act a bit like a diode, which will be another lesson. But basically what these are used for, normally with one of these, I'll tell you what it do for this. Normally this will act as a very, very high resistance, like 1,000,000 ohms, while the voltage across is below a certain point. So you might have one that's designed, for instance, to have like a 1,000,000 ohms until the voltage across it reaches 115 volts, yeah? Once it goes above 115 volts, this drops to a very low resistance. And effectively that will short out the 115 volts coming in and blow the fuse, and sometimes blow this up. This would be used, I'll give you an example, whereby say you've got a circuit where it has a switch. You've seen power supplies, the older ones, had a switch on the back, and you select 240 volts or 120 volts, yeah? And if you select 120 volts and plug it into 240 volts, you're going to damage something, you're going to blow something up. If you're lucky, it's just a fuse, but you probably won't be that lucky, you know. So these are used in that type of circuit, for example, so that when you set it to 110 and you plug it into 240, 240p is over here, this effectively goes short, blows a fuse and probably destroys this at the same time. So they're like a protection device, and that's basically what a varistor is. Most commonly you see them is when they've blown up. Right, let's have a look at a few other things. Yeah, variable resistors. That, is that a broken? That's a broken one. Okay. Variable resistors. What you got here, basically, is a little horseshoe shaped or U-shaped carbon track, yeah? And this has 503. So that's 50 and 3 zeros. That's another way to mark resistors. 50000. So in colour codes, this would be green, black, orange. But this is up at 50000. Yeah? And that is the resistance between this end and this end. 50 kilo ohms, 50,000 ohms, yeah? But you'll see with this, there's a third leg here, yeah? And that third leg is connected to this little wiper here, because it's like a little wiper. And that wiper goes along with this track, yeah? And by... I'll find something that's got a flat edge, yeah? I'll probably find a screwdriver in a minute. Because this, will this do is save even picking another... You know, don't use a proper tool or anything like that, because I can turn that, yeah? So by turning that, you're changing the resistance from both ends to here. So from both ends to the wiper. So the more it's turned that way, yeah, the more the middle one's connected to this, and the more it's turned the other way, the more to this. That's a variable resistor. You used to see them more in older circuitry, but yeah, you might come across these things, especially in audio equipment. I've seen them in a few more modern things, disco lasers as well, and a few things like that. But that's a variable resistor, and quite a small one. We also get variable resistors that look like this. I'm going to go back over to the desk cam now, because some of these components are getting a bit too big to look at in the microscope. But you've seen all the interesting ones. Get variable resistors that look like this. Again, this will be marked on it, on the back or on the side. 10, can you see it in focus? Bit odd to focus on the camera, but that's 100 kb. So 100k, that's 100k, 100,000 ohms, and that'll be the resistance between the two ends, yeah? This little shaft turns. So inside here is just the same as that thing I showed you with the carbon track. That's what's inside, yeah? And the middle one will either connect to that end or this end or somewhere in between. So the resistance between there and there and there and there will vary. Often used on old equipment as volume controls, tone controls. That's what's behind, you know, the knob that you used to have before we all went much more digital and touch button. There's another one. That's another variable resistor. If you see this, it's 2, yeah? 1, 2, 2 gangs. So in here, there's 2 variable resistors controlled by the same shaft, yeah? B100k, 100,000 ohms. The B won't be a tolerance on this. I'll tell you what the B is. And this one was B as well, 100k B, yeah. When you have resistors like this, you have 2 main sorts. There might be more than 2, but you have linear and you have logarithmic. So with a linear, say that's 100 kilo ohms from there to there, yeah? If I switch the wiper to this end, from there to there is 0, yeah? If I switch it to halfway, it's 50 kilo ohms. If I switch it all the way, it's 100 kilo ohms. If I go 3/4, it's 75. If I go 1/4, it's 25, yeah? It's linear. So the same amount of movement will always add or decrease the same amount of resistance. The other tool, B, a logarithmic. And this works on the logarithmic scale. So like, if I move it, say, 10%, that'll go to whatever value. Let's say it goes to 10, yeah? If I move it by another 10%, it adds 100 more. If I go another 10%, it adds 1,000 more. And so on, yeah? It's a logarithmic scale. If you're interested, look up logarithmic scales, but that's what that is. Logarithmic ones are commonly used in audio equipment. Commonly. Because of the way you hear music. I won't get to the complicated stuff, that's what they're used for. If you want to know more, go look up logarithmic, yeah. I think B's logarithmic and A's linear, I'm not sure. This one, last one of these, then we looked at enough resistors now. This one's marked again. Can I see the markings on that one? Not enough light. Oh, it's upside. Oh no, not the right way up. V50K AK2. Yeah. 50K will be the value. This is a slider resistor, which is just the same thing as that, but goes in a line. Yeah. These twin gang ones, by the way, often use a stereo, so it alters both channels at once. Again, this is twin gang, so you've got two connections at both ends. You've got two lots of sliders, which are in here. And you can, these little ones here, there's no connection on them, they're just like little tabs to hold this in place. So inside here, there's actually two carbon tracks, and this is a little brush that moves up and down the tracks and alters resistance. Mixers, a lot of these are, you know, DJ mixers, even today you'll see them in there. So yeah, that's a good look at some resistors. So hopefully now you know to actually recognise a resistor when you see one. Oh, just a little bit more. I've only shown you the through-hole ones there. There are also surface mount ones. This definitely needs the microscope again. So let's go over back to the microscope. Okay. 0805 10 ohm SMD. And you can see them there in the little bag. Yeah, I can get one out. Why not? Let's get one out and have a look and see what they are. Okay, so they're still in a little plastic thing, and I'll leave them in there. Look, you can see they marked 100. Yeah, no, they're not marked 100. They're marked 10, and then the next 0 is no 0. So 10 times 0 is 10. Yeah, if you saw 101, that'd be 10 and 10, and the following zeros. That's 100. Yeah. Make better next example. Now you understand this. If you see 102. That's 10 and 2 more zeros, so it's 1,000, 1 kilo ohm. Yeah, 103, 10 and 3 zeros. That's 10 kilo ohms, 10,000. So that's how they're marked. The other marking for these is this code here, 0805. That's the size. So basically, for an 0805, these are 8mm by 5mm. Yeah, that's the size. That's the size. That's the value. And you see the markings now. So the first two are the value. So imagine if I'll show you another one, maybe a bit more. So let's do one again. You know, so let's not just do this one. So let's get another one. Yeah. I won't tell you what value this is. See if you can work it out. There we go. 151. What value do you think that is? 151. Well, I've just told you. So I really hope you can get that right. Yeah. But 151. 15 is effectively the value, and 1 tells it's followed by 10. So 151 is 150. Yeah, 152 would be 1,500, and so on, as I just explained. So that's surface mount resistors. This is probably one of the larger sizes you'll come across. You'll come across some much smaller ones of these. And just tied up. I'm just putting back into the little plastic bag. Yeah. 1 moment. Right. So that's those. That's the 0805s. The ones I keep in stock, I'll come to that in a minute. I'll tell you basically what I keep and how it's best to get some of these things. These are 0603s. So these are 6mm by 3m, whereas the first one was 8 by 5. Yeah. One moment. Okay, guys, just somebody at the door there. Okay, I'll just show you now. I was going to show you this. I've got all the resistors out now. These are the 0805, yeah? This is the next size down, which are 0603. Yeah? These ones are, I think these are 0201, you know. I bought them as 0402, but there's a bit of confusion between imperial sizes and metric sizes, yeah. So these, I'm sure these are 0201, which is 2mm by 1mm. Those are about the smallest I can handle normally with soldering. The next ones down from that one, I can solder. I mean, I'm just going to decide what size these are. 06, no 06, about 0805, 0604, 0402. Next one down from that is 0201, 2mm by 1mm. 0201 is the smallest I can comfortably solder. There are some that are half the size again. 01005, which is like 1mm by half a millimetre. I personally find that sort of stuff difficult, but I haven't had much experience really, so I'm not saying it's not doable. I'm not saying I can't do it. It's just that, you know, for my own comfort zone, those 0402s are the smallest I really like to work on. You know, you get it down to like specks of dust basically after that. I don't know if there's anything smaller than the 01005. Maybe somebody can add on the comments actually. Okay, so those are surface mount resistors, which obviously you see a lot in modern equipment. Okay, let's go back to the desk and let's have a look at these resistors. Move that one. There we go. Let's get in there. Okay, so we can see the paper. Right. First of all, let's talk about the symbols. So what have we seen in the way of resistors? Yeah, resistor. Yeah. So the symbol for a resistor I've just shown you is either that or it's that. Yeah, and the markings are like I've shown you. 1R0, which is 1 ohm, 1 ohm. Yeah. 1K5, 1.500, 1500, 1M8, 1.8 mega ohms, 0.8 mega ohms. So you know that's how they are. But mostly you'll see this 1R0 type, 1K, and 1M. But I showed you a few resistors. You can see there's a bit of variation. So that's a resistor. Next one then. Variable resistors. Variable resistor, two symbols again. I've got a feeling, I think this is the international one and this is the American one. Maybe somebody can tell me if that's correct. Yeah. So that is a symbol for a variable resistor. So this basically is the slider. Yeah. These again are marked in the same way. I showed you some. You found like 100K. You'd often find ones that say B or A. This will be a linear or logarithmic scale, so that's how they normally marked. Then what else do we have? We have thermistor. Yeah, thermistor. Thermistor is symbol normally like this. You see this much more commonly like this, yeah, like that. You can see it like that as well. That's a thermistor. The thermistor is a resistor that the value of the resistor depends on the temperature. You find NTC, negative temperature coefficient, and PTC, positive. This will go down in resistance as the temperature goes higher. This will go up. That's by far the more common one that you find. And normally to stop inrush current on the mains connection coming in. That's that one, yeah. Varistor. This has a very similar symbol. Again, the one at the top is the more common that you see. Like that, yeah. Like that. This is the one that effectively is a very high value until the voltage across it reaches a certain point at which it becomes a very low value. And this is for surge suppression, especially for protection where something might be plugged into the wrong input voltage. So if that happens, this effectively goes short, and it probably destroys itself. It'll certainly blow the fuse, but it'll protect the expensive device. Yeah. This one sometimes has another symbol. You'll sometimes see this symbol. Yeah. All those are varistors. Just to confuse matters, sometimes a thermistor is marked like this, the same as a varistor. In fact, if you remember the disco light, or if you saw the disco light video, you saw that we had, you know, it was I said that's a thermistor, but the symbol's actually a varistor. So that's that one. The other common one that you see, no, they're not common, they're uncommon. Yeah, I used to see these a bit more in the 70s and 80s, but the only time I've ever seen these is like in independent. It is in the electronics kits where you know you play with, that you learn, you can buy for kids or adults who want to learn the electronics. Yeah, and the symbol for this one is well, we can draw it this way. That you often see, strangely enough, this one you often see like that. I mean, any of these symbols, by the way, you can see them that way, yeah, depending on how they draw on the circuit diagram. Light dependent resistor, unlikely to find one of them unless you're interested in getting one of these electronic kits to play with, well, to learn from. Yeah, so that's that. Those are the main type. One more type of resistor I need to just mention to you, and it's not one resistor, it's a matrix. You see there's a lot on motherboards and that sort of thing. Yeah, I've got some matrices here, but these are not the type you normally see in the motherboards, maybe on older motherboards. These are matrices, yeah. So what you effectively got on here, normally they'll have one common leg and then all the rest of the resistance to that leg. So this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, yeah, 5, 6, 7, 8, 9, 10. This might have 1 or 2 common pins and then maybe 8 internal resistors. So effectively what you have here on a matrix is something like this. A common pin and resistors connecting to it like that, yeah? Like that sort of thing. And this, although it's drawn as a rail, will just be one pin on here, yeah? You often see these in motherboards where you have like a data bus and address bus, and they're connected to as a pull-up, what they call pull-up resistor, so that when the bus is not being driven, it's pulled up to whatever the voltage of the bus is, whether it's 3 volts, 5 volts, 1 volt, or whatever it is, yeah? So you'll see them. The more common, I haven't got one to show you, the more common these days looks like this. So you'll have, looks like an integrated circuit, like 4 legs here and 4 legs here. I should always draw the legs first and draw the box afterwards. So you have something like this, and inside it, let's make it a bit bigger so you can see what it is, yeah? So something like this, often with 8 legs, but again it could be something else, yeah? Inside it, effectively, there's 4 resistors like this, yeah? Again, they're commonly used as pull-ups or pull down to 0. This end will go to voltage plus, whatever it is for the data bus or the signal bus, and then these will be connected to various signals. So you'll see them. They can be very small. They can be very, very small, those. And on the circuit diagram, it will be marked as 4 resistors like this. And it might on the schematic, because just a little bit more about schematics, yeah. A resistor on the schematic will probably say R, so you might find R802, R406. These are not values, it's just resistor number 406, R1, R2, yeah, R44. So that'll be printed on the circuit board. If you have the circuit diagram, you can look up on the circuit board and see where the resistor is that you're interested in, yeah. Variable resistors are normally marked as VR, VR1, VR2, and so on, yeah? Thermistors, sometimes TH. Varistors, I can't think of what the common, I don't know, might be VA, but I wouldn't even be certain of that. Next time I find the circuit board with a varistor on, we'll have a look and see what it is, yeah? Light dependent resistors, if it has, it'll be LDR1, LDR2, and so on. And these resistor matrices are usually marked as RN, resistor network. So you like RN34, RN48, that's this sort of thing, yeah? Again, this is not a value, this is just the number of the components on the circuit diagram, and you can see where it is on the board. Okay, so that's plenty about schematics and resistors. Let's talk a little bit about what they actually do, yeah? So get rid of that one. The main two uses of a resistor really are current limiting, yeah, and what's called a voltage divider. So talk about those. A current limiter basically is a resistor that's going to a load, yeah, to ground, to volts in, yeah. So I say 12 volts, yeah. So there's 12 volts, and if your load only needs no more than 10 milliamps, yeah, then you can work out the value of this resistor. So it's VIR. We keep looking back at this one. We want to know the value of the resistor, so it's 12 over 10 milliamps, which is 0.01 amps. And that goes into there 1220, 1200 times. That's doing the maths in my head, I hope I'm right. So a 1.2 kilo ohm resistor there will give you the required current. You don't need to know the maths. You're not, unless you want to start circuit designing. All you really need to know is that resistor there is there to limit the current, and the value of the resistor will be chosen to give the current that the designer wanted. Yeah, that's one of the uses for resistors. The other usage of a resistor is what's called the voltage divider, where you have commonly two resistors like this. Yeah, call it 12 volts again, and this goes to somewhere. Yeah, in your circuit. And if, for instance, like you wanted 3 volts on here, then basically you choose these resistors. So this is a quarter of that one. So if this was like, say, 1200, will this be 300? Even sometimes I can't even do the maths. I'll tell you what, let's make one or two. Let's make them and let's see how they work. That's a good thing. Resistors in series. Again, you don't need to know this maths. If you really want to work out what these components should be, just go and look it up. I think that's right, but I'm not a circuit designer. I just know what stuff's supposed to do, yeah? You can go and find a website, put resistors in series, and you can put your values in, put your voltage in, it'll tell you exactly what's on there. You don't need to work it out if you don't want to. Okay, resistors in series. Say we get 3 resistors like that in series, yeah? And this is 1 KO, 1000 ohms. Yeah, they're all 1000 ohms, yeah? What's the resistors from there to there? Do you know? Can you work out what it is? We'll measure it, but I know what it is. We'll measure it and we'll prove it. The other thing you can have is resistors in parallel, yeah? You'll commonly see both of these, so you need to know this. This is something you do need to know. Two resistors like that, 1000 ohms, 1000 ohms. What's the resistance between there and there? Again, I know, but let's measure it. Let's do it. Let's actually do it practically, yeah. And then we'll come back and we'll explain what the formula is. Okay, so here we have some resistors. These are 1000 ohm resistors, brown, black, reds, 1000 ohm resistors, yeah. And we'll make this circuit that we had here, and we'll just do it by twisting the legs together, yeah. 1, 2, 3, yeah. Three resistors. There's our circuit, yeah. And we'll get our ohm meter. Ohms. And we'll measure the resistors from here to here. And we have, nearest damn it, 3000. Yeah. 3000. So 1000 from there to there. It's close enough, yeah. They have a tolerance. 1000 and 1000. And the total is 3. Yeah. So for resistors in series, the total the resistance you see is the sum. It's that one plus that one plus that one, yeah? 1000 plus 1000 plus 1000 is 3. That's simple, isn't it? Let's have a look at the other circuit. What have we got here? I've got a few more resistors. What are these? Yeah. These are yellow, purple, brown, I think. Let's see what they are. The yellow, orange, brown. 430s or... yeah, 430 kilo... no, 0.43 kilo ohms. 430 ohms. Yellow, orange, brown. 430. Nearest, damn it, yeah? Let's make this circuit. So we have that circuit, yeah. Let's see, what do we get now? We got 215, which is half. Okay, as well as 1k ohms. Let's change this. These are now 430 ohms, yeah. And this is now 430 ohms. And what I see between there is half of that, 215 ohms, yeah. There's actually a formula for working that out, and you know, I can't remember the formula anymore. It's 1 over something plus 1 over something. We'll look it up on the internet. Or if you're interested, go look up the formula for resistors in parallel. I can't remember because I don't need to use it anymore. I just know that if you've got more of these in parallel, the answer is less than what, you know, half or a quarter. And these resistors can be different values, and you'll get, you know, a different result. So that's them, yeah. I told you we weren't going to do any maths on this channel. Let's not do maths. We don't need to do maths, yeah. That is an interesting thing. This is the 3 in series. Now I said to you, one reason for resistors is current limiting, yeah. Most very common reason you see is current limiting. I've now lost my pen, of course. Too much stuff on the desk. Current limit, yeah. The other common reason is what's called a voltage divider, yeah. And this is a voltage divider. So let's see what that does, eh? Again, there's maths if you want to do the maths. There's formulas that will work this stuff out, but we don't need that. I'm going to connect here across these resistors here my power supply. I've set the power supply to 12 volts, yeah. So now across here is 12 volts, and we can get the multimeter, and we can see from here to here. When you can see the multimeter. When I turn the power supply on, we'll call that 12, eh? So from there to there is 12. So what do you think will be, there's 3 of them, what do you think will be across the first one? It's a 1 kilo ohms. 4, yeah? What do you think is down to the next one? 8. So across each of these is 4, because the resistors are all the same value. Yeah? 4, 4, 4. That's like I drew here, yeah? So if you've got 0 volts here and 12 volts here, here you will have 8 volts, and here you will have 4 volts. It's like a ladder, yeah? And these are all the same value. The amount of current flowing will depend on the value of those resistance. Let's get rid of one of these resistors off here now, yeah? Just take that one off there. Let's get one of our 430 ohm resistors, yeah? And let's stick the 430 ohm resistor on here. So we still have a voltage divider, but that's 1000, well that's 1000 and that's 430. What do you think we'll get now? What do you think we'll see? What do you think we'll see across all three of them, end to end? You should be able to answer that one. What was he from end to end? It's put it that way around, eh? It's 12 volts because it's 12 volts coming in. What are we going to see across this one now? 4.9. A bit more. And what's across this one? 4.9. And what's across this one? 2.1. So we have 12 volts, yeah? Ground, 0 volts, yeah? 1k ohm, 1k ohm, 430 ohm, yeah? And here now we had, was it 2.9, 3.9? Let me measure it again. 4.9, 4.9, 4.9 volts, 4.9 volts, and the last one is 2.1. Yeah. Basically, roughly speaking, that is a bit less than half of that, yeah? Because it's a 430. If that had been a 500 ohm that we had there, yeah, then I can tell you this would be half of what on one. So over 500, you get half of what you got on the 1000. Well, it's a bit less than, you know, so we get a bit less than half, yeah, a bit less than 2.5. So that's basically how that works. The lower in the chain like this, the lower the resistance, the lower voltage will appear across it, and that's basically a voltage divider. You'll see these quite often in circuits. Again, look, there's maths, there's a formula that will calculate it, but if you're like me, like you're a repairer, you don't really care about how it was calculated. You just want to know if it works or not. And you can see yourself, if you see a circuit, something like this, 12 volts, yeah, 10k, 1k, yeah, you can tell straight away there's going to be about 10 times as much voltage across that one as there is across that one, so it's 10 times as big. And that's probably good enough, you know. So you can say, well, if there's one here, it's going to be a bit more than one. There's going to be 10 there, doesn't quite add up. So you say, well, that must be about 1.2, and this must be, that's 12 then. So it's probably something like 1.1 volts here. You can get a good idea of what it would be there, yeah. And then 10.9 here. I don't know if those are correct, but you get a formula. But it's good enough. You know full well the voltage there is about a tenth of that. And if you can't quite work it in your head, you can just go and look up resistors and series, voltage divider. And again, you'll find a website where you just put the values in and it tells you exactly what you got. So that's that. So we're almost at the end of this video now, but I just want to have a bit of fun. Let's have a bit of fun. So I promise you we'd have a bit of fun with this. Is there anything else I want you to talk about? Is there anything I missed out? I made myself some notes. No, I think we've covered all that. Yep. Right, this is the important bit. And you've heard me mention watts before. You know, resistor, which is so many watts, so many ohm, and now you're going to see why that is. So, let's find, where did I put it? Light bulb. A light bulb's a resistor, basically. It's a resistor, you know. It's just wire in there. We use usually I think tungsten as a filament. Yeah, tungsten. And we stick 12 volts on that, and it basically the resistor gets so hot it glows. And the only reason it doesn't burn that's because of vacuum in here. So that is a light bulb, but it's a resistor. Now let's find another resistor. I had some just the ones for this. Yeah, where are they? Resistor, yeah, it's drawing 1.75 amps. That is. I'm just looking on my power supply. So, one more bit of paper. we have the light bulb. Yeah, that's symbol for the light bulb, roughly speaking. 12V, 0V, 1.75 amps. Yeah, and we can calculate that with Ohm's law. What is the resistance of the light bulb? So let's have a quick look at the resistance of the light bulb. Let me go onto the screen capture. Let's have a quick look. Calculator, yeah. So we know there's 12 volts across each, yeah. And we know that resistance equals V over I. So V is volts divided by 1.175. The resistance is about 10 ohms, yeah. Thereabouts of that light bulb. So we can think, okay, let's go back to the camera again. We can think, okay, we've got a light bulb, yeah, 12 volt, yeah. What if we want to dim that bulb and make it a bit dimmer? Can we do this? Yeah. And we know that's about 10 ohms, so let's put a 10 ohm resistor here, because we know, roughly speaking, if that's 10 and that's 10, that's 12. This punt's going to be about 6 volt, yeah? So it's going to be 6 volts across this resistor and 6 volts across the bulb, and it should come on off brightness, yeah? So, okay, let's do that. I got one earlier, a resistor about the same, right sort of value. So, we've got a light bulb, we've got a resistor, yeah? And we just need another crocodile clip lead, yeah? And then we're going to connect our resistor, and we're going to connect it to the light bulb, and we expect this to then come on half brightness. Just 1 second. Okay, just customer calling at the door there. Okay, so we've got a circuit, we've got the light bulb, we've got the resistor, yeah? And we were thinking if we put 6 volts on there, it'll come on and off brightness. So let's have a look, see what actually happens when we do that, yeah? I have the wrong value resistor because nothing's happening. What value is this resistor here? What have I found? Is that a 10 ohm resistor? I don't think so, because nothing happened. What we got? Oh no, it's like a 600 K. Why did it say minus? 50 kilo ohms, that's much too high. We need a lower value resistor than that. Well, I'm sure I found one somewhere. Let's have a look up on my desk of bits here. If not, well, let's just go find one. So we want a resistor about 10 ohms, yeah? Let's find one. This is a 7.5, so it'll come on a little bit brighter than half, yeah. So let's connect our resistor there, and we connect our resistor there, and we connect the power, and now it should light up at half brightness or thereabouts. Okay, here we go. Oh dear, what's happened here? Can you see that smoke? It came on for half brightness for a couple seconds, and our resistor is now toast. Why did that happen? Well, the reason that happens is this. A resistor resists current, yeah? And I'll put this like this. You've got a hill, yeah? And you've got a car going down the hill, yeah? Let's draw a car. Noddy car. 1940s noddy car. So we've got a car going down the hill, yeah? And you want to slow it down, you want to resist the movement. So you put the brakes on, yeah? What happens to the brakes? Well, you should know, they get hot. But normally they design so by the time you take your brakes off, they cool back down again. But if you're going down a lot of steep hills and you keep putting the brakes on, eventually you get a burning smell coming from the brakes because you're overheating the brakes. And that's what happens to the car. Well, the resistor is the same. When the resistor, and there's a lovely smell in here now, by the way. When the resistor resists, it generates friction like your brakes, electrical friction like your brakes develop mechanical friction, and the resistor gets hot. And the reason that resistor burnt out was this. We've talked about volts, amps, current. We've talked about ohms, resistance yet. There's one more we need to talk about. Watts, after Watt, another scientist. Volta, ampere for amps, ohm for resistance, and watt, yeah? And watts equals voltage times current, yeah? So I told you that light bulb was taking 1.75 amps, yeah? And when there was 6 volts across it, 12 volts across it, yeah? So now a circuit, there should be about 6 volts across it, yeah? And you'd expect the current to go down to about half of this because we've added more resistance. So the current for this to be half brightness is going to be half of that, which is about 0.85, something like that, 0.85, close enough, amps, yeah? And the voltage across that light bulb now is about 6 volts, yeah? So the wattage is 6 times 0.85, which, without getting my calculator out, is somewhere between about 5 watts, yeah? And that resistor I used was like a quarter watt resistor. So this did what your brakes did. The brakes weren't powerful enough. You come down the hill too fast and the brakes just burnt out, and that's why that resistor just fried. And that's why you have resistors like this one. Big chunky resistors, yeah? Because this is a 10 watt resistor. So if we use this resistor and do the same thing, we'll connect to power, and we'll, there's a light bulb, yeah? And we'll connect the power to here, and now see what happens. Not a lot. Huh. Because I've connected the wrong lead, that's all, Luke. I've connected the wrong lead. I haven't connected the lead to the light bulb, of course. So. Okay, power in to the light bulb to the resistor, and there, yeah? And this is our 10 watt resistor. Now what happens? Well, yeah, the light bulb now comes on about half brightness. This is getting warm, but not overly hot because it's designed to handle up to 10 watts, and it's dissipating about 5 watts. This is why things like this have bigger pieces of aluminium that you bolt to a piece of metal, yeah, for 100 watts. That's quite warm now. So that's watts. That's the last thing you really need to know with resistors, voltage and current. I think that's the end of that one. Hope you've enjoyed it. Hope you had a bit of fun when we burnt up that resistor. Why not? It's all part of the fun. And hope you, if you liked it or didn't like it, you know, get in the comments under the video and let me know what you think. Anything that wasn't clear, we can talk about it more. And I'll see you guys and girls on the next one.